Now, our second question is a question about limits. More precisely, the limit of quantum mechanics in which it becomes, quote unquote, classical mechanics. Now, many of you may already be familiar with this quote. This is from Dirac's famous textbook, that classical mechanics may be regarded as a limiting case of quantum mechanics when Planck's constant h by 2 pi tends to 0. Now, in reality, things are really not that straightforward. For example, there are plenty of situations where this kind of classical limit cannot be taken at all, or if they can be taken only in a very specific way. Just to cite one example, if you look at the total scattering cross-section from a hard sphere of radius r, the classical result is very straightforward. Classically, when you look at a hard sphere head-on, you get to see its cross-section, which is just a circle of radius r. And so the total scattering cross-section, in this case, for hard spheres is simply pi times r square. On the other hand, the quantum result, at least in a simple low energy limit, is exactly 4 times that. Taking h cross to 0 does not change that at all. In a sense, it seems like the wave nature of the particles being scattered allows them to sort of scan the entire surface of the sphere, not just look at the cross-section, which is why you can sort of understand why there's a factor of 4. But notice that in this case, no matter what limit you take, you are not going to get the classical result back. Well, a situation where things are slightly more clear-cut, at least apparently, is that of time evolution, sorry, that's a typo, and I did the wrong thing. It's a time evolution that we are talking about. Time evolution of expectation values. Well, once again, most students would be aware that Ehrenfest's theorem apparently answers that in the positive. Just to remind you, we start from Schrodinger's equation. You can get these results about the expectation values of position and momentum. Rate at which the position's expectation value changes is equal to the momentum divided by mass. Rate at which the momentum's expectation value changes is given by the expectation value of the negative of del V del X, which of course, as you're all aware, is the force. And sticking to one dimension for this, you can have multidimensional extensions of this result. Now, this looks exactly like the classical equations. In classical physics, we know that the rate at which position changes is momentum by m. That's, of course, the definition of momentum, mass times velocity. And the rate at which momentum changes is minus dv dx, del v del x, which is just the force, Newton's second law. So it looks, at least on the face of it, like the fact that this equation, ddt of expression value of x is expression of p by m, and the second one exactly mimics the classical equations. The real question is, do they really? And to see that the answer is not really yes, let us take an example. Suppose we talk about the quartic and harmonic oscillator, where the potential is x to the power 4, unlike our familiar harmonic oscillator, where of course the potential is proportional to x squared. Now, in this case, if you use the Ehrenfest theorem, the left-hand equation, of course, stays the same. It's independent of the potential. The right-hand one tells you that the rate at which the momentum changes, or rather the momentum expectation value changes, is minus lambda times the expectation value of x cubed. Now, let's look at the classical formula. The classical formula, as expected, looks exactly the same, except for the fact that in the quantum formula, you have expectation values. In the classical formula, you have actually x and p, the variables. However, there is one big catch. Here you have lambda times the expectation value of x cubed, which is not the same. Despite the fact that this looks like expectation value of x and expectation value of p obeys the same equations on x and p, expectation value of x cubed, which is there on the right-hand side of the rate of change equation, for the momentum expectation value is not the same as the cube of the expectation value of x. And as a result, these two are different equations. If this had been, if the equation for the expectation value of p had been d dt of expectation value of p is minus lambda expectation value of x whole cubed, then of course there would be no problem at all. But here, they are really different equations. So even Ehrenfest's theorem, which apparently tells you that the classical equations for expectation values exactly match, the quantum equations for expectation values exactly match the classical equations, don't really say that. There is one exception, however, and that's a very important exception for us, which is the harmonic oscillator. For the harmonic oscillator, the potential is quadratic. And hence, the equations which Ehrenfest's theorem gives you are actually linear equations. ddt of expectation of x is, of course, as always, expectation of p by m. But ddt of expectation of p is simply minus m omega squared times expectation of x. And now, this exactly matches the corresponding classical equations. And so, expression of x and expression of p for a harmonic oscillator, no matter what the state is, always obeys the same equations that you expect the classical formula variables to do. So expression of x at time t is expression of x at time t0 times cosine omega t minus t0 plus, this is the v by omega sine omega t minus t0 that you're all familiar with in the standard classical solution for a harmonic oscillator. And the expression of p similarly has exactly the classical evaluation formula. However, there is a big difference between classical mechanics and quantum mechanics, even for the harmonic oscillator. And what is that? Well, for energy eigenstates, remember these are stationary states. In stationary states, things don't evolve with time. So expression value of x at time t stays whatever it was at time t0, namely 0. And the momentum expression value also vanishes. Again, a result which should not be unfamiliar to any of you. But we just found that the expectation values for harmonic oscillators, eigenstates, whichever states you are talking about, would always oscillate with frequency omega. However, this is not really inconsistent with that result. This is consistent with the classical behavior. After all, if you do not disturb a harmonic oscillator from its equilibrium position, then its position and momentum stay 0 at all times. So there is nothing really non-classical about these results. Of course, these are results for the expectation values for quantum systems. But as we have just said, Ehrenfest's theorem guarantees that for the harmonic oscillator, the classical values will be obeyed. They are obeyed here too. However, this will completely defy the classical connection that we know between the amplitude of the motion and the energy of the motion. We know that the energy of the motion, which is entirely potential when the particle is at one end of its motion, is given by half m omega squared a squared. There is no kinetic energy at the end point. Total energy is just exactly equal to the potential energy there. So that's what we have. Notice that when you are in a harmonic oscillator eigenstate, the energy eigenstate has an energy given by n plus half h cross omega, which can be pretty large when n becomes large, pretty large compared to, say, other quantum systems, I mean. But the amplitude of the oscillation is still 0. So this equation, the classical equation between energy and amplitude is not valid at all. The gap between the two, E minus half m omega squared a squared, among the energy eigenstates is closest for the ground state, simply because the energy is the smallest there. Half m omega squared a squared is still 0. E for the ground state, where n is 0, is of course half h cross omega. So this is the smallest you can have among energy eigenstates. The closest energy gets to half m omega squared a squared. The question that we are asking here about this limit, where the classical theory behaves the same way as quantum theory, would be, can we get closer? That is, can we make this gap smaller than half h cross omega for a harmonic oscillator? And can we do that when the amplitude is not zero? We can do this for the ground state, but then the amplitude will be zero. So the expectation value of x and expectation value of p will not change with time at all. The question is, can we have time varying solutions for expectation value of x and expectation value of p, where we can come at least as close as this or maybe closer? So that is our second question.